Okay, well, welcome everybody to College of Science Virtual Seminar. I'm Michael Kaufman, Dean of the College of Science, and today we're very happy to have Professor Aaron Romanowsky from our Department of Physics and Astronomy. He's going to tell us about the dark side of extreme galaxies. Just a little background on Aaron. Aaron got his, let's see if I get this right. He got his undergraduate degree in physics from UC Santa Barbara, then went on to Harvard where he got his master's and his PhD, and then stayed at Harvard for a little while as a research fellow. And then Aaron, I think, gets the award for most well-traveled postgraduate scholar that I know of. From Harvard, he went to the Kaptein Institute in Groningen, the Netherlands, then to the University of Nottingham, on to the National University of La Plata for just a short visit. That's in Argentina. Then to the Department of Physics at the University of Concepcion in Chile. And then spent about 5 years as a researcher at the UC observatories at UC Santa Cruz before joining San Jose State as an assistant professor in 2012. He's in the very short time that he's been here, gone right through the ranks. So he's full professor now. He's winner of the San Jose State University Early Career Investigator Award, a Cottrell Scholar, and an all-around pretty amazing scientist and teacher. So very happy to have him here. As usual, once we get the talk started, you can put questions in the chat and we will interrupt Aaron if it looks like it's something that needs to be interrupted for. Otherwise, we'll leave the questions to the end and you can ask the questions yourselves. So without further ado, Aaron, please tell us about the dark side of extreme galaxies.
All right, thanks, Michael, for the kind words. Yeah, just said maybe I have an example of what persistence can do for you. Not giving up on the career pathway until you get there. Multiple postdocs, and very glad to be here at San Jose State. Very supportive environment, and I'll be talking about here a lot of work that's been done here at San Jose State and collaborators regionally and throughout the world. I won't have time to point out all of them, but I'll do a few highlights as I go. So I'm going to be talking about extreme galaxies and explain what I mean by that as I go. First, a little background on just a big picture of galaxies. This, some of you may recognize this picture as our nearest neighbor, a large galaxy called the Andromeda Galaxy, also known as M31 by astronomers. It's a large spiral galaxy, very similar to our own Milky Way galaxy that we live in. And if we could see our galaxy from the outside, fly our drone all the way out at 100,000 light years, then you might see a picture roughly like this. So probably a lot of you have seen pictures like this of this large galaxy, but you might not have noticed anytime you have a picture of a large galaxy, you might get these other smaller things in the image. The specks of light all across the image are foreground stars in our own Milky Way. So just if you ignore that, you'll see these couple other smudges here, which are smaller dwarf type galaxies. There's M31 Andromeda Galaxy. There's a dwarf elliptical galaxy. It turns out to be one of the most numerous types of galaxies in the universe. This one is actually the opposite. It's a very rare type of galaxy called a compact elliptical. For many, many years, that was the only one known. It happened to be in our local group, our local neighborhood. And I'll come back to what that thing actually is. Up here is another thing I've marked called the Fornax dwarf spheroidal. It's not, it's a companion to our own galaxy. I've just kind of put it there for comparison. Another numerous type of dwarf galaxy. You can see it's kind of a low surface brightness galaxy. You might be barely able to see it. However, in addition, there is something I kind of fibbed about these dots here. They're not all stars. There's a few of them. And I'll get to that. Just to say as a point of scale, the sizes of galaxies, this RE is a radius of the galaxy called the effective radius. Their sizes are kiloparsecs, are 100 quadrillion kilometers in size. Now, if you zoom in, one of these dots turns out not to be a star at all. That's what's called a globular cluster. You can see it's a collection of stars, say 100,000 to 1 million stars, all in this dense ball, very densely collected on the scale of about a parsec. So that's about 3 light years or about 100 trillion kilometers, nearly that much. So there's the scales of galaxies, kiloparsec scales of these globular clusters of parsecs, and all large galaxies have these globular clusters, including our own. There's still somewhat of a mystery where they come from. And I'll come back to later to why I'm even mentioning these globular clusters before I talk a little more about galaxies and the physics of galaxies. So going beyond the beautiful images and now starting to measure the physical properties, including mass, a very basic property of anything. And what one can do is use orbits. This is a schematic diagram. You might have seen it in intro astronomy or physics class of a circular orbit, radius r, and an object in orbit has a velocity v, acceleration a, and you can consider this the sun with the Earth orbiting it. You might measure the velocity. Now imagine you're not looking at the Earth around the sun, but another planet around another star. You might measure the velocity of the system through spectroscopy. So a lot of what I'm going to be talking about is going beyond imaging and using spectroscopy. You take a spectrum, you see the different spectral lines from different elements or molecules, and you see a shift to the left or the right. It's called the Doppler shift. You measure the velocity. Once you measure that velocity, if you know the radius, then you've measured the acceleration. You use Newton's laws to set that acceleration equal to Newton's gravitational acceleration. And it looks like this, there's the centripetal acceleration on the left, gravitational on the right. Do some algebra, you turn it around, and there's the mass. If you can measure the radius of the orbit and the speed of the orbit, you've measured the mass of your central object, which becomes important. There's a lot of things in the universe you'd like to know what the mass is. So that could be a planet around a star, measuring the mass of that star. It could be stars going around a black hole and measuring the mass of the black hole. It could be gas in a galaxy orbiting, and then you're measuring the mass of the galaxy. Or it could be galaxies within a cluster of galaxies orbiting, and you're measuring the mass of the entire cluster. Just to say that I've started off with this very simple schematic of a circular orbit here, and in real life, things are not always so simple. You can have more random or quasi-chaotic orbits, and what you tend to use is not just a simple v, but a velocity dispersion, which is should be the square root of the mean square velocity from statistical mechanics. And of gas, you might recognize this kind of notation, and you can link that kinetic energy to the potential energy through what's called the virial theorem. So I'm not going to get into that in any more detail, but just to say in practice, this is can be quite a bit more complicated than the simple schematic for measuring the mass. So here is now a little more in practice of measuring a spiral galaxy like the Milky Way, measuring the speed of gas and stars going in a approximately circular orbit around that galaxy. This is a map of gas, and it's color-coded by the redshift and blue shift. So you can see by eye that you're seeing an inclined disk, and you're seeing the red and the blue rotation, and you can get an idea of what direction it's rotating and how fast. And you would expect that as you go out to the outskirts of the galaxy, you'd expect what's called a Keplerian rotation curve, that if using this Newtonian gravity, as the gravity falls off, then your rotation will gradually decline as 1 over the square root of the distance. Now, the big surprise started in the 70s was when people went out and measured rotation curves, is they didn't exactly do this. And Vera Rubin is pictured here. She was one of the pioneers, and there's a big observatory being built now named after her, the Vera Rubin Observatory in Chile. And here's a measurement of a rotation curve of another galaxy. And this declining curve is what you would have expected to see from the gravity falling off. And the actual measurements, it just stays flat. The velocity stays flat. And this was a surprise. It turned out to be observed in many galaxies. It's constant flat rotation curve. And then if you convert that constant velocity to a mass, then what that means is the mass is constantly increasing as you go out beyond the galaxy, and beyond where you can see stars and gas. You expect to, like, you've reached the end of the galaxy, that should be it, that's all the mass, but the mass is still increasing. And that's what we call dark matter. And schematically, you can't see dark matter, but if you could, it might look like this, a fog of material enveloping a galaxy beyond its visible extent. And not just around each galaxy, but between the galaxies. You see these tiny little dots of light here are galaxies embedded in a cosmic web of dark matter pervading the universe. So what is dark matter? Well, dark matter is maybe a misnomer. You might call it invisible matter. And it's anything that has mass but no detectable light. And that's historically has been a lot of different things that fit that category. Just say that if you lost your socks in space, that would be dark matter. You probably couldn't detect the socks. maybe with a thermal emission, depending on the temperature. But more seriously, other things that could be dark matter, if you put them far enough away, planets, low mass stars, cold gas, black holes, neutrinos, a lot of different kind of things that we know about, but it would be hard to detect. And for a while, up until the 90s, those were leading candidates for what the dark matter might be. And various experiments and observations ended up ruling those out. So those kind of bog standard things are not the dark matter. There is still kind of a ongoing idea that there might be primordial black holes formed shortly after the Big Bang, could be a component of the dark matter. But the standard picture is that this is some kind of new particle, kind of like the neutrino is a particle with a mass that is very hard to detect. And this other dark matter could be an exotic particle, kind of like a neutrino that only interacts through gravity effectively. So the leading candidates for this, for many years, it was what's called the weakly interacting massive particles, or WIMPs, which is that's a motivation and supersymmetry theory. And I've crossed that out because there is some worry that that's not the right particle anymore, and I'll come back to that. Another candidate, which is possible, it's called an ultralight axion, or fuzzy dark matter, and I'll come back to that a little bit later. Sterile neutrinos. And there are many detection experiments for different types of dark matter all across the world. This is one example called the Lux-Zeppelin experiment in the upper Midwest. And basically, these detectors are buried far in mines far beneath the Earth's surface to shield out other background particles and try to detect some rare interactions from dark matter. This is a schematic which I'm not going to have time to go through, but it's basically an illustration of many experiments over the years trying to measure dark matter and pushing the limits of detection down where they still haven't detected it, different masses, different cross sections, and have ruled out a huge area of parameter space for what this particle could be. And this is the reason I've crossed out the WIMPs, because basically they ruled out a lot of the possibilities for WIMPs. It's still possible, but it's getting more and more difficult. And people are turning to other candidates as also likely possibilities. So dark matter, that was the lab. You'd ultimately like to detect it in the lab, just like neutrinos were detected in the lab. But for now, our only way really to study it is astrophysically through its gravitational effects on things in the universe. And through that, which I won't have time to go through, we've determined that it seems to be about 85% of matter in the universe. So it's the dominant component, massive component of the universe. And that matter is what pulls the galaxies together. So I'm going to show a video here, a computer simulation called Eagle of the universe starting off as a fairly homogeneous sea of gas and dark matter. And what this is we're seeing dark matter particles in the simulation as if you could actually see them. And you see they start from a diffuse homogeneous distribution to this filamentary network structure. Now it's lighting up the gas, which is following these dark matter filaments and collapsing into nodes and collisions. And then they start forming larger and larger structures in galaxies and clusters of galaxies. So what you see here is this constant merging. This is from, it's about 5 billion years after the beginning of the universe. And we're going to come up to, now we stopped about 8 billion years ago. And you've got a proto-galaxy forming. So imagine this could be our own Milky Way galaxy. You can see it looks kind of like a spiral galaxy rotating, the gases coming in, and continues to flow in up until the present day. And the galaxies look majestic and grand and steady, but actually they're constantly on galactic timescales. They're constantly evolving, constantly changing, accreting material, blowing material out, very active and energetic. And that's, as you can now see this in the simulation, up to the present day, a Milky Way type galaxy.
Aaron, can I ask a quick question?
Mm-hmm.
In these simulations, is this just gravity, or is there physics in it too? I mean, other physics, cooling, radiation, things like that.
Yes. Yeah, you can do different types of simulations. The simplest one would be only gravity, and you learn a lot about how the dark matter forms into these filaments, basically only under gravity. But when you get to what I showed here with the gas flows, you definitely need other physics, all the hydrodynamics, all sorts of radiation feedback and supernova feedback, black hole feedback, and that's where the complexity is of the cutting edge of understanding is. There's a lot we still don't understand about galaxy formation because of the details of this physics.
Thanks.
Thanks. And this is now you can see a present day distribution of dark matter. You get these galaxies with dark matter, these clumps with dark matter in between them. And the bottom line is that in this picture, galaxies, each galaxy typically has 30 to 300 times as much dark matter as they have in the stars that you can see, is our expectation and what we measure in most galaxies, as far as we can tell. Let's see if I can advance this. Okay, so I'm going to move on to kind of a different way. I've been talking about mass. Now I just want to go back to talking about visible galaxies that you can see and surveys of galaxies that have measured and classified them over the years. Two basic properties. This one down here is M is for magnitude. It's an astronomical term. It's a log of a luminosity. So the physical scale is here, log luminosity, and half-light radius is the size of the galaxy on log scales. So our Milky Way galaxy is about 10 billion solar luminosities. So it's over here, and the size of around a couple kiloparsecs, 2,000. So it's right around here in this area. So you can see there's some larger galaxies, and then there's these smaller ones called dwarfs, dwarf ellipticals, and dwarf spheroidals. This kind of sequence of galaxies, and ours is one of the largest. It's much more populous. They're not. There could be way more dots I put in here, but just schematically, you can see these dwarf spheroidals. And then out here, I put these globular clusters, and this was kind of 20 years ago would have been a silly plot to make, because it's plotting apples and oranges together. You wouldn't put galaxies and globular clusters on the same plot. There's a clear divide between sizes and luminosities, and the globular clusters are orbiting the galaxies. They're just a different category of object, but there's a reason I put those there. And partly you can start seeing some clues. There are a few oddballs that are already known around our own galaxy, called Omega Centauri, which is something you can see from the southern hemisphere, and a couple other large ones that are luminous and unusually large for globular cluster. Okay, they're kind of in this range of, say, 10 parsecs or more, and about 1 million solar luminosities. So this kind of field took a new direction about in 2013, when this new type of object was recognized, and I'll show. Actually, it was before that, but this is from 2013. This is a Hubble Space Telescope image of two large galaxies, the spiral galaxy here, and elliptical. And it turns out that there's more than you can actually notice here. This object here is, you would have thought it was a foreground star. It actually turns out to be a tiny little galaxy. And it's bright enough that if you go back 100 years and you look at an image from Edwin Hubble took, it's sitting right there and is plain as day, but no one would have thought that that was anything remarkable until you have the high resolution of the Hubble Space Telescope, where you took a spectrum. And this turns out to be an example of what we call ultra compact dwarf, very dense galaxy orbiting these larger galaxies, about 40 million solar luminosities, the size of about 25 parsecs. For comparison to that Omega Cyn, I pointed out earlier as like a large Milky Way globular cluster, unusually large. This is much larger, but still not as large as a galaxy. And this class of what we call ultra compact dwarfs, or UCDs, were discovered about 20 years ago. And the question then immediately posed was, well, what are these? Are these largest star clusters, or are they the smallest galaxies? And once this one I pointed out that was fairly easy to detect once you knew where to look was found, here in San Jose State, we started thinking, well, what could we do? These are not very hard to find. You just have to know what to look for. And so a couple of undergrads got together and started searching for these in public databases, something called the Sloan Digital Sky Survey. It's not as famous as the Hubble Space Telescope, but just as important in many ways, because it has this uniform map of the sky, both photometrically and spectroscopically, with a publicly accessible database, which means in principle, you could just get on your phone and make a discovery, which I think they didn't literally use their phones, they used their laptops, but they could have used their phones. And you get like interfaces that look like this, and using some more advanced search queries, you can also run through this archive and find, and this is what Richard here on the right found, is this another ultra compact dwarf, even brighter and denser than that previous one I showed. And then we did all sorts of follow-up on these with imaging and spectroscopy. So here is another view of that. Here's the object down here, and we got Hubble Space Telescope images of Richard's object. And just to confirm exactly what it is, its properties, it's the new densest galaxy. Michael was working on kind of a separate side project and found something else that is still confusing us to this day. We're not sure if this is a galaxy or not. We're calling it a hypercompact cluster. It's the densest free-floating system that we know of, but even Hubble has difficulty telling the difference between this and a star, a very dense system. 10 million solar masses packed into a 2 parsec radius. So This is a kind of an image of what you might see from the surface of the Earth on a dark night. If you could look up, you see a few thousand stars to the naked eye. If you were on this a planet in one of these dense dwarfs or star clusters, it would look like this, about 1 million stars you could see with the naked eye, assuming your eyes weren't fried from all the exotic objects, black holes and neutron stars, white dwarfs spewing energetic radiation in this area. So if you now start populating that plot I showed earlier from 20 years ago with these new discoveries, you can kind of see that things are starting to fill in. Now you no longer have a clear boundary, a gap between the galaxies and the star clusters, but these gaps are starting to be bridged. And ultra compact dwarfs, extended star clusters, compact ellipticals, and then you start asking the question, now that there's no clear gap, how do you know where the galaxies stop and the star clusters begin, if there is actually a difference? And how do these things form, these unusual objects? So here are 3 types of stellar systems: a giant elliptical galaxy on the left, a globular cluster on the right, ultra compact dwarf in the center. They're all different zoom levels, but just to say that they're round masses of stars of similar ages and roughly similar compositions. Well, how would you tell the difference? And you try to think to yourself about, how would I tell the difference? Basically, if I want to know this one in the center belongs on the left or the right. And just as a clue, they say probably this one in the center, if it is a galaxy, probably didn't form that way. It probably used to be larger and got stripped down to a nucleus. So some ideas are, well, let's look for dark matter as a hallmark of galaxies, but not star clusters. Look for dark matter around this thing. Let's see if it has a central massive black hole, and I'll get to that. Let's look at the populations of stars in that, see if it resembles more on the left or the right, or the orbits around the massive galaxy is another clue, or any other ideas. If you have ideas, get in touch, because we're still trying to figure out some good diagnostics here to tell the difference. So I mentioned the black holes, and just to show as a bit of background, this is an animation of the center of our own Milky Way galaxy based on work by Andrea Ghez and collaborators at UCLA. Andrea won the Nobel Prize, or shared in the Nobel Prize last year for this discovery or confirmation that there's actually a black hole, supermassive black hole at the center of our galaxy. And what you're seeing here is reconstructions of orbits of stars around the galaxy. And normally stars in the galaxy take 100 million years, order 100 million years to go around the galaxy. Here at the center of the galaxy, some of them are going so fast that they circle in around 10 or 20 years. And so it means on human lifespans, you've already seen complete orbits or nearly complete orbits using various large telescopes, such as the Keck telescope in Hawaii. And so you can see them zooming around very quickly, some central, very massive collection or point mass. And that is the hallmark of a supermassive black hole. It doesn't seem to be anything else. And you can actually measure curvature of space as predicted by general relativity for those orbits getting close enough to the black hole. Very exciting. And the mass of that black hole is about 4 million solar masses. It sounds like a lot. It's actually a little bit on the small side relative to what some other galaxies have. So as people have now over the years been measuring other galaxies, you can't get that level of detail in other galaxies, but you can measure the velocities of material at the center of galaxies. It turns out that basically all giant galaxies have a supermassive black hole. Some of the dwarfs do, and that's where a lot of active interest is in figuring out how many dwarfs and which types of dwarfs have black holes or not. And when I say supermassive, that's around a million to a billion or 10 billion solar masses. A couple of years ago, there was a famous discovery from what's called the Event Horizon Telescope. It's a radio interferometer zooming in right on the center of this massive elliptical galaxy nearby. It's called M87, center of the Virgo cluster, and seeing this bright ring here. And what you're actually seeing is the shadow of the black hole. That dark patch at the center is the shadow of the black hole, with the ring being hot material circulating around that black hole. And this was the lead scientist on reconstructing the image that seeing that image for the first time was a very happy moment. This is an artist's picture of what could be at the center of these galaxies of hot gas circling the center of a black hole and then shooting these polar jets out very far. You can actually see by eye this jet shooting out from the center of M87. And here's another artist picture. If you could really get close to the black hole, there's a gravitational lensing effect predicted by general relativity, where the background stars, you'd actually get warped images close to the event horizon of that black hole. So this now brings us to the question of, okay, if these ultra compact dwarfs that we've been discovering lately were nuclei of larger galaxies, then those galaxies should have had supermassive black holes, and they should still have them if these galaxies are stripped apart. The black hole is the last thing to go. So let's go out and look for the gravitational effects using now not the Hubble Space Telescope. It's actually ground-based telescopes are better for this type of observation, using laser guide stars to help counteract the turbulence in the atmosphere to get a really crystal clear view of these. And what you see here on the left is a heat map of orbital velocities at the center of this ultra compact dwarf. This is Richard's dwarf that he discovered here. And you can see this hot spot here right at the center, which is the hallmark of the black hole. On the right here is a model reconstruction with a black hole included. If you didn't have the black hole, basically you wouldn't have that hot spot. And so we confirmed that there is a black hole in the center of this with a mass of 4 million solar masses. So this is this tiny object with a black hole as big as our entire Milky Way's black hole. And even that, it's about 2% of the mass of the galaxy. Some other ultra compact dwarfs have even more massive black holes than that. So I call this a smoking gun for this having been a stripped galaxy, that it still has this massive black hole. We can't see any other way to get a black hole like that in there. And it's a natural consequence if it were a stripped galaxy. So this is where I want to switch over to Michael, who was one of the students who found this these unusual galaxies. Wasn't content just to do the observation, but actually to make a computer animation here using physics. Let's see if I can turn that down a little bit. And this is a video game rendering image engine called Blender, using Python under the hood to do a simulation of a tidal stripping of a galaxy. You can see it happen very quickly. The smaller galaxy fell into the big one, and it's being stripped apart, and the stars are being dispersed around that larger galaxy. But you see this little compact blob at the center. That was the high-density nucleus of the original galaxy, which is resistant to gravitational ties. Its own internal gravitational force is strong enough to keep it together against the gravitational field of that larger galaxy, and basically stay there indefinitely. It's now just in orbit as this compact satellite galaxy of the larger one. And we're going to stop and just kind of zoom around, pan around in 3D. And then we're going to do a mock zoom in to this object. And flash to like, this is the actual image. We imagine we could zoom in farther and see the supermassive black hole. And imagine you're on the surface. Right. So we should go back to the other. So after Rich and Michael discovered those two, we kind of realized, wow, we're really onto something. Let's make this a cottage industry at San Jose State. Something students can be very productive in, and various students over the years have found similar types of ultra compact dwarfs or compact ellipticals, mostly the latter, and have these published. And also working in an area called machine learning of how do you recognize these objects? Sometimes they're very hard to tell the difference between other things like background galaxies or foreground stars. This is where machine learning comes in, and trying to discriminate between the different types of objects, which I won't have time to go into detail, but various teams of students over the years have had fun finding these galaxies. We have a new band we're forming called Ultra. So, okay, that was the kind of my first half of the talk, which is these ultra compact dwarfs, the first kind of exotic galaxy. Well, the question is, what else is out there lurking? You know, we think we know what types of galaxies are out there, spirals and ellipticals and these certain dwarfs, and here's something new, ultra compact dwarfs. Well, what else could we be missing? And just keeping in mind that it's very hard to see things out there observationally sometimes. This is okay, I don't know if anyone recognizes that. That is the hood ornament from a Subaru car. Well, why does it look like that? Subaru turns out to be Japanese for what we call the small collection of objects we call the Pleiades. It's the Greek name for it, the Seven Sisters. And for some reason, the founder of Subaru must have liked that constellation and put it on the hood ornament. Well, I mentioned that because one of the telescopes we've been using is the Subaru telescope, the Japanese telescope on Hawaii. which is not sponsored by Subaru, but it's named after the same stellar system. So here's an image of a coma cluster of galaxies. You can kind of maybe see these are large spiral elliptical galaxies here, these large smudges with a lot of empty space in between. Well, we know it's filled with dark matter. This is actually the first place dark matter was discovered in 1933 by Fritz Zwicky. But with a deeper view with a Subaru telescope, I've changed the image stretch. Now you can start seeing some things in between. These little smudges here of very low surface brightness faint dwarf galaxies. So as you increase the depth of your imaging, you start finding more things. So this is not so much that they're dense and hard to see that way, but that they're very faint or low surface brightness. And this led to a discovery that I was not on the original discovery team, but got involved later of what we call the fluffiest galaxies. And it's gotten some press because of that. And this is this team that used this new technique.
One on tape, so we're not smiling.
Oops, sorry, I seem to have a autoplay on YouTube. Okay, back to there. Using these telephoto lenses that have a special coating on them to reduce the reflectivity of the light that comes in. And it turns out that seeing these low surface brightness objects is not, you don't so much need a big telescope. You need a telescope which is very good about minimizing things like scattered light and glare and other artifacts. And so this technique using these telephoto lenses has been very powerful for discovering this new type of low surface brightness object called ultra diffuse galaxies, which turn out to be pervasive, not only in the Coma cluster, but in other places throughout the universe. This is a Hubble Space Telescope image of one of the near examples, and you could call them ghost galaxies because you can see through them. So here you've got the collection of stars, but you can actually see galaxies in the background behind there. This redshifted large spiral galaxy, for example. Now, if we have one in the local group, which would be fun, and you put it side by side with the Andromeda Galaxy, it would look like this big fog of stars, which is almost the same size as this large spiral galaxy, but way fewer stars, about 100,000 times less. Similar amount of stars to these dwarf galaxies over here, but spread out over this much larger region. So luminosities like dwarfs, sizes like giants, which again raises the question of how do you categorize this, especially if you think about its dark matter. This dark matter halo could be who knows what. Maybe it has a dark matter halo that's more like a large giant galaxy. It just has hardly any stars, and it's not a dwarf galaxy at all. And that's one of the interesting questions. Just as a preview of what's going to come later, that it also has globular clusters in there, which is to a degree which is surprising for a dwarf galaxy. So now if you start putting this on a size plot, I've cut off the globular clusters here. Again, size, luminosity, this is the standard galaxy sequence. These ultra diffuse galaxies are in this population here of these large sizes, lower luminosities. And these turn out to be the ones that are the most interesting. They're old, been sitting around for 10 billion years, apparently in the Coma cluster, and we're not sure where they came from. There are some found out beyond clusters we call blue or gas-rich ultra-diffuse galaxies, which I won't discuss, but they might just coincidentally have similar properties and not be the same thing. So if you could be inside of an ultra-diffuse galaxy and look at the night sky, you might not even know you're inside of a galaxy, a few stars in the sky that's very sparsely populated. Okay, so how are these things made? Now that they're discovered, a lot of activity in trying to figure out where do these come from, what are they? And there is kind of a very standard recipe for making them, and which we think is happening to some degree. Here's another image in the X-rays of another large nearby cluster called the Perseus cluster of galaxies. And it's filled with hot gas and got all sorts of effects as galaxies fall into it. It's a fairly well-known series of processes that happen to those galaxies as they're disrupted and transformed. Here we got what we call a blue ultra-diffuse galaxy falling in, and you see it's kind of irregular. It tells us maybe the gas is being perturbed strongly as it falls in, and it leads to another one perhaps like this that becomes like a red UDG after it's kind of lost its gas and the blue young stars have expired, and you have this old red and dead galaxy. And we call this vanilla recipe for making an ultra-diffuse galaxy, is that you've got these dwarfs that fall in, they get what we call quenched, they lose the gas, and the stars die out. And there are different effects that can cause them to become big as they fall in. Tons of papers written on this, and it kind of seems like a solved problem. Okay, but is that the only way to get these ultra-diffuse galaxies? And there are some clues out there that there's something else going on. One of them is we have a few examples of these things found beyond clusters of galaxies, just sitting out there on their lonesome and without gas, without young stars. And that kind of violates what we think we know about at least dwarf galaxies, that they have no way to shut off their star formation. The giant galaxies have these supermassive black holes that will do that. These ones don't, but they're old and red and dead. And so it's a big puzzle of how these things fit in with that standard picture I showed. The other thing is, as I mentioned, some of these have a lot of globular clusters, a subset of them do. You hear some where basically you can hardly even see the galaxies. All you see is these dots of the globular clusters associated with them. So that a huge fraction of their mass is actually in these globular clusters, and considering globular clusters actually disrupt with time, that could be 100% of them were formed basically a collection of globular clusters which form a galaxy without forming the normal population of galaxies like a disk, a spiral galaxy. We call these pure stellar halos. And I call this recipe the half-baked galaxies, the failed galaxies. These things formed early on with some globular clusters and then just stopped 10 billion years ago for some unknown reason. And if that's true, then you can make predictions. You say, well, then that means that they probably have a lot of dark matter because the dark matter continues to collect gravitationally. And the stars should be unusual properties because they're just these old ancient stars. And for that, we need deep spectroscopy to go out and study these ultra-diffuse galaxies. Entering the Keck telescope, the world's most powerful optical telescope on the ground in the big island Mauna Kea. Up until recently, we've not been able to go out there and observe in person. It's been remote lately, but this was before that with various trips I've done with the students out there as a reward for finding useful objects as they get to go out to Hawaii and follow up. This is one of the couple students going up to the summit to visit the Keck telescope, and that's the control room down at below the summit. We're remotely operating actually on the island. We had clouds and we tried to observe Saturn, actually still saturated the CCD, where we're observing the compact ellipticals and ultra diffuse galaxies with spectroscopy using this new instrument called the Keck Cosmic Web Imager. It's what's called an integral field spectrograph. Can't really go into all the details, but it's a way of capturing a lot of light and mapping out things in 2 dimensions spectroscopically. So this is what some of the data look like of one of these ultra diffuse galaxies. You can see a spectrum here. You can measure spectral lines and magnesium, hydrogen, iron lines, and I'll come back to some results on that later. Here's another example of a very deep spectrum. Again, you can measure the depth of these lines. You can measure the redshift and the width of these lines. It's Doppler broadening will give you the idea of the mass. So from those results, we ended up having some really interesting findings that have come out in different press releases and news stories. I'm going to talk about a couple of these. The dark twin. So the first is, after running through taking mass measurements using the dynamics, using Doppler shifts and Doppler broadening, you're able to estimate the amount of dark matter in these galaxies. And we're still struggling to be really sure about how much dark matter there is because there's some extrapolation involved. But our best estimates so far are that some of these ultra diffuse galaxies have about 10 times as much dark matter as they're supposed to if they're just normal dwarf galaxies. So this is a schematic picture of stellar mass of the galaxy, telling what you can see, and then the halo mass is the dark matter of what you measure or you infer. And there's a kind of a standard picture here, a sequence of the dwarf galaxies and these ultra diffuse ones. Some of them seem to have this more massive dark matter halos. And the other thing we've been measuring is these stellar populations, or the ages and the chemical or atomic content of these galaxies. And there's some key clues about as galaxies continue to build up, they enrich their elements as stars explode and pollute the gas around them and form new stars. There's more and more richness of elements. So really low abundance of elements like iron is a clue that these galaxies, the stars, are very ancient. And so some of these same ultra diffuse galaxies have very low in iron, which tells us they're more primordial. So they're consistent with this picture of being these primordial fossil galaxies from the early universe. And one of them is very strange. That's this blue one out here, which I call it the anemic galaxy. It's very extremely low in iron, and it has this weird high magnesium abundance, which tells us something about early supernova history. And we're struggling to explain the properties of this galaxy. It must provide some clue as to how these things are formed, these ultra diffuse galaxies. So one of the other interesting things you can do with these is because they're very dark matter dominated systems, these ultra diffuse galaxies, is you can measure the dark matter properties or how it's distributed. And this gets us back to the very beginning when I talked about what could the dark matter be. One of the possibilities is this thing called fuzzy dark matter. It's ultralight scalar boson. It's extremely low mass particle, 10 to the minus 2 electron volts, which using the uncertainty principle in quantum mechanics, then that tells you when the low mass object has a certain scale called the de Broglie wavelength, of which it has a fluctuation on the scale of galaxies, that basically these particles are so low mass that they're not localized on the scale of entire galaxy. And that would be an interesting way of explaining a lot of properties of the distribution of dark matter around galaxies. It also predicts that that these things will collect in a bump, we call a soliton bump at the center of the galaxy, and create this distinctive feature that we can try to detect through these dynamics. Okay, and won't go into the details, but that's kind of what you can look for these ultra diffuse galaxies. So we did this. This is again a heat map of the stellar kinematics of one of these ultra diffuse galaxies. You can kind of see by eye, it's red on the outskirts, it's blue in the center. So it is cold in the center. You don't see this heat bump in the center that you might expect to see. And through more detailed modeling, we can't necessarily rule out the fuzzy dark matter, but we can say that if it is there, then we can put a constraint on what that particle mass is. And so we get this is like probability distribution of the log of this particle mass in this 10 to the minus 2 eV scale. So it's this between 1 and 10 times 10 to the minus 2 eV, which turns out to be consistent with what's inferred in some other galaxies. It's inconsistent with other large scale inferences for this dark matter particle if it exists. So basically we can't exclude that it exists, but the implied mass that we would get is in tension with some other constraints. So it's kind of pointing away from this being the candidate, which of course is not fun. It'd be nice if we could confirm something like this, but so far it's not looking good. There are some possible ways out for this. This theory is not dead yet. So this other type of ultra diffuse galaxy that we had in the news is something I'll talk about. It's even more exotic and more controversial. And here it is popping up in a story in The Guardian and also in Fox News, one of these rare situations where both news sources are agreeing on something. A different type of ghost galaxy. And we didn't know that we were going to find this. Again, another surprise. So we initially called this the blob. It's this ultra diffuse galaxy very nearby. And we were looking for another one where we could measure its dark matter to try to do things like test fuzzy dark matter. And this seemed like a great candidate. Very nearby, it has lots of what look like globular clusters. When we measured the speeds, it turned out instead of being unusually high speeds, they're unusually low speeds of about 5 kilometers per second. Just to put that in perspective, I don't know if you might recognize that. That's Elon Musk's Roadster leaving Earth into a solar system orbit. And orbits in the solar system are of order 5, 10, 30 kilometers per second. That's a relatively low speed. Inside of a Milky Way, the speeds are about 100 kilometers per second. A dwarf galaxy is more like, say, 50 kilometers per second. So that's a very low speed. So low that there's no suggestion of dark matter there. It's hard to rule out dark matter to kind of disprove that something missing mass isn't there, but so far there's no evidence for it. It seems very unusual. And if these were the first galaxies that Vera Rubin had studied, she would not have found the dark matter, or anybody else for that matter. So we've had a couple of examples of this now. This appears to be a new family of ultra diffuse galaxies with very low velocities. And the interesting side effect of this is that by having no dark matter, that's kind of a strong indication that dark matter actually exists. Okay, so let me explain that a little bit. As I mentioned, that because dark matter hasn't been tested yet, one of the obvious has not been verified yet through like a laboratory detection, for example. One of the obvious alternatives is that, well, maybe there isn't any dark matter. Maybe it's the gravity, what we call Newtonian gravity, breaks down on large scales, just as in weak field limit, just in the strong field limit, like around a black hole, it breaks down and becomes general relativity. Maybe there's something else happening on these weak field acceleration scales, which are not really testable in the lab. There's various theories about this, things like modified Newtonian dynamics or extensions to general relativity. And the consequence of that would be that there will always be this kind of phantom dark matter effect anytime you go out to the outskirts of a galaxy. You can't do away with it. It's a fundamental property of gravity. Well, that's very different from dark matter, which you could, in principle, extract the dark matter from a galaxy or not have it, and then you would have no evidence for this gravitational anomaly. You can't do that if gravity itself is different. So by having these rare galaxies with no dark matter, then that's kind of evidence for dark matter existing in the other cases where you see this gravitational disparity. Okay. Anyway, back to these galaxies. Now the question is, okay, there's been very controversial whether it's really correct that they don't have dark matter or not. And it still seems to be holding up the more data we get on it, more analysis we do. And then it starts raising the questions of, well, how do these things form? I say the most standard picture is that these are tidally disrupting dwarfs, that they used to have dark matter just like any normal dwarf. They fell into a larger galaxy, like I showed in that animation where they strip off the stars. And actually, you're also stripping off the dark matter as that happens. And you're not left with a dense nucleus, but you still are left with this dense, the central collection of stars that could have lost most of its dark matter. So that is possible. It seems to be contrived in these cases, and there's some other evidence against that. So it's not, that's the really kind of standard picture. I think it's probably not right for all of these. And so it starts bringing up some more exotic ways for creating galaxies, that you could have collisions of gas which form the stars. And so just like you need gas to form stars, you don't directly need dark matter to form stars. So as I showed at the very beginning, the really standard picture now is that you need dark matter to form galaxies, to bring gas together to form stars. It's sort of this indirect effect of the gravity of the dark matter. Well, in principle, you don't need the dark matter in the first place if you can find a way to compress the gas to form stars. And you could get that through gas collisions. You could maybe get that from black hole outflows of jets from the center of the galaxy could compress the gas clouds. These are very exotic scenarios for forming galaxies, and it'd be very interesting that some galaxies are forming in this different way. So we don't have conclusions. This is kind of cutting edge now of trying to understand where these things are coming from. But we would like more examples to understand the phenomenology better and put more constraints on the theory. So like I showed that there's 2 examples now. We're really on the hunt for more, at least a third one. I'll come back to that in a minute, but just to mention that, interestingly, it seems like these ultra diffuse galaxies, some of them they seem very similar in appearance on their imaging, that they're very different when you study them in more detail. So this one on the left, I could call it's a shadow galaxy because it's almost entirely composed of dark matter. The one on the right, I call it the vampire galaxy because it has no shadow. It's no dark matter, it's only stars. And it just reminds us that, keep us humble and keep us amazed that as we look in the universe, we continue to discover more things that we never suspected. And astronomy continues to be in a golden age because we keep finding new phenomena. So yes, we would like to find more examples of these interesting exotic galaxies, and students here at San Jose are very active currently, and some other ones that we're following up with Keck, with the Hubble Space Telescope, also working with Spitzer data to find and analyze more of these objects. And I'll just close with a beautiful image of a globular cluster in our own galaxy and ask for questions.
Wow, that was a great talk. Thanks so much, Aaron.
Thank you.
So Michael had to leave, which is why I was on the, sorry, there we go. Michael had to go to another function. And so that's why I've been on the call, so that I could take over at this point and help out with questions. And so everybody, if you have questions, please go ahead and either put them in the chat or in the Q&A. And I am going to take this moment while everybody's trying to collect their thoughts and ask my questions, which are very naive, being that I'm a biologist. But so is the idea of dark matter, at least from your work, that you need it to basically compress, I think this is what you're saying, but let me know if I'm correct, is to compress gas to form galaxies, and it's providing this force to like draw it all together. But if you have some other force that can perform the same function, then you can have these galaxies that actually don't have any dark matter at all.
That's right, yes. Yeah.
And so then is part of that, would part of your goal be then to start discovering more of these galaxies that don't have dark matter, and then showing that there was some other force that could have done dark matter's job there. Is that something you would pursue?
Yes, exactly. Yeah, that's one of the things. If we could find a couple more examples, part of it is we're using circumstantial evidence to try to have some constraints on how these things formed. For example, those two that are known with no dark matter originally seem to be orbiting a giant galaxy, and it becomes natural to think that is an effect of that giant galaxy one way or the other. We've done some more work now that it looks like they aren't both orbiting, which is kind of a surprise. And so basically, if we can find these things that are actually isolated, not around a large galaxy, it tells us that they formed on their own without some external effect or were rejected somehow. And so we're bringing in like kind of more circumstantial evidence about how they might have formed. But right, we're trying to figure out like if you could find one actually forming, I mean, because like there are galaxies we observe in all sorts of different stages of formation. And if we could find one that's actively forming through this process, that if we could tell, then maybe that would be a way to know. But basically, we're just trying to figure out some clues to see what the formation process was. And by finding more of those types of galaxies, then it gives us more clues and more constraints.
Wow. Yeah, that's really interesting. I just want to ask one more question, then we'll open it up to the other group. You mentioned that you were using machine learning to try to discriminate between some of these bodies that you're discovering. Mm-hmm. And I know you said you wouldn't have time to talk about it, but maybe you could take a little moment now to say something about that project and how it's going.
Yeah. Well, I've had some students in the past experiment with machine learning to see if this would work. That basically the idea, one way to think about machine learning, it's a way of analyzing multidimensional data space. That you can start with something that's a very simple. It's like, let's look at the luminosity and the size of an object and try to find things that fit in certain region that are like certain brightness and certain small size and try to see if that's an ultra compact dwarf galaxy, for example. But there's other properties too. There's colors, there's different wavelengths of light, they have different colors, and there's multiple colors. And there's like other different details of the shapes. You consider like, say, 10 dimensions of properties of those galaxies, those objects, which both becomes difficult to analyze in 10 dimensions, but it also gives you more leverage for saying like, okay, you have the multidimensional space and things can really isolate once you have multi-dimensions to isolate different categories. And that's where machine learning comes in. It's a way of kind of analyzing that multidimensional space. And we've experimented with that a little bit and haven't got it to work yet, but I think there's still a lot more to do, especially as more databases come along. I mentioned the Vera Rubin Observatory at the very beginning. There's this massive telescope nearly ready in Chile, first light, I think in 2 years, which will be this brand new survey of the sky, which will have much better data than the Sloan survey that I showed earlier. And that's where machine learning will be really important to try to work on those data sets.
Wow, that's fascinating. Michael is texting in a question. So let me read this for Michael. Are there other dark matter distributions that could mimic no dark matter?
Yes, it's interesting. I mean, it's hard to rule out that there isn't dark matter where we're not looking. For example, when we're measuring the velocities of stars in a galaxy, you're measuring the dark matter basically in the visible part of the galaxy. In principle, you could have dark matter outside of that, and you have like a donut hole distribution of dark matter. There you get into something that's maybe not only it could be unstable, or it could be physically implausible. Like, how would you get a donut hole dark matter distribution? You could get kind of something in between what's called a chord distribution. And that's part of, to get dark matter models to work at all in this case, with a tidal stripping, you have to invoke what's called a chord. It's something has depressed the density of dark matter, and that could be a supernova feedback effect, for example. But even that doesn't seem to work. You kind of need to have this special dark matter distribution to start with, then the tidal disruption, which will depress it even more, unless you have a donut hole, but there's no a priori reason to get a donut hole distribution.
Okay, well, we have a question in the Q&A, and this is from Tommy Wen Chin, and I'm going to see if I can let Tommy ask question. Let's see, allow to talk. Okay. me try that again.
Hi,
Okay.
can you guys hear?
Yes, I can.
Hi, Dr. Romanowsky.
Tommy.
Really great talk. I have two questions, and they're kind of different from each other. And the first one is do you suspect if there are various types of dark matter, as in if there's only one type, then when we discover it, do we discover all dark matter at once?
Yeah, no, it's a good question. And the answer is, well, we don't know. There's actually hundreds of candidates for different possible dark matter particles. So why couldn't we even have hundreds of types of dark matter? And the answer, I think, is just we have to start somewhere. Occam's razor would say, like, whatever, maybe there's only one type, and let's look for that. And we'd be happy to find one type. If we do find more than one, that's fine as well. And when I say type, that these are all, and I didn't talk about it, it's called a cold dark matter, which is a non-relativistic type of particle. There's a certain class of dark matter particles, but it could be multiple particles. We'd like, just for simplicity again, to have it be one thing that's emerging from theory of like why there's this one pervasive dark matter particle, but there could be more than one.
Okay, yeah, that makes sense. Thank you. My other question is, based on the theory where we think of dark matter as a new particle and it having a wavelength of about 1 kiloparsec, would that be quantum mechanics at an astronomical scale?
Yeah, exactly. That's what that is. It's the de Broglie wavelength. It's this matter oscillation on astronomical scale that's not localized. And that would make it very hard to detect in the lab.
Well, that would be really exciting. Well, thank you.
Thanks, Tommy.
There actually are lab experiments for that. There are other consequences of it. And I know some people even locally are working on that.
Wow. Our next question is from Satinder, and I'm going to go ahead and allow Satinder to ask the question. And Satinder, are you able to unmute and talk now? Satinder, are you able to unmute and talk? I think I can ask to unmute. I'll just try that. If it doesn't work, it says, sorry, I can't talk. Okay, so I will read the question then. It says, what role does dark matter play in the expansion of the universe? Since they seem to be doing opposite things, will the expansion negate dark matter's effect eventually?
Yes, interesting. The expansion, yes, the dark matter does have a contracting force that it wants to work against the expansion. And what's interesting is there seems to be an opposite force, an anti-gravity force that's pushing the expansion. It's called dark energy, which I didn't mention at all. And that's even more mysterious than the dark matter. I really don't understand what the dark energy would be. Of course, there are theories. And it turns out that's more dominant than the energy density of dark matter is actually the dark energy. And some people call it the double dark picture of the universe, dark matter, dark energy, which dominates. And what we are, our normal everyday material atoms are 3% of the universe, and everything else is dominating on large scales. And right, that expansion, we're not really sure the long-term expansion, exactly how that's going to go. But right now it's driving against the dark matter contraction.
Awesome. Well, thanks for that question, Satinder. Okay, well, let me just look and see if we have any more questions. I think you have answered them all, and exactly on time almost. We went only 2 minutes over, which is really good for us. So I am going to thank you, Aaron, so much for such an exciting talk, and invite everyone. I sent out the link for the College of Science Happy Hour, and Aaron will be there, so you can come and ask all of your dark matter questions. So thanks so much again, Aaron, and everybody, please come join us at Happy Hour.
Oh, there is a possible question there.
Oh, is there another question?
Christina had her hand up, but she's gone now.
Oh, Oh, she did. Oh, so sorry I missed that. Well, hopefully she is on her way to happy hour to ask that very same question. Okay. See you all soon.